Hello, grade 12s. This next lesson is on rate law. So we're continuing discussion on kinetics in chemistry. We have looked at a few different ways to express how a reaction changes rate, how individual components of the reaction, such as reactants and products, can change, and how we can express those. So as review, right, we looked at the individual expression of each of your reactants and products. We looked at, make sure that's clicked. There you go. In a reaction, let's say a general reaction, that is A plus B produces C and D. Our individual expressions for each of these products looked like A, lowercase b, lowercase c, lowercase d. These are our balanced coefficients. We saw that you can relate each of them in a certain way where your reactants are all negatives, and we'll just do a couple. And the rate of change of the concentration of A can be expressed in this way, delta T, and this is related to, let's say, D, where it's a positive value, right, over the coefficient, and again, the rate of change of the concentration of D, right? This is not, rate law is not this. Rate law is not that. Rate law will refer to the overall rate of the reaction, right? We looked at the individual rates and how they can relate to each other in a certain way. This is right for what we talked about last, but this is different from your overall rate law. Okay, continue to make that distinction as we move on, right? So here we find that the concentration of any individual reactant, so that's a key point here, of any individual reactant has varying effects. Right, so this varying effect is not dependent on the balanced coefficients, not dependent on A, B, C, or D. Right, so the overall reaction has varying effects based on the reactant itself. Right, and then if we therefore change the concentration of the reactants in our general reaction, A may affect the rate in certain ways. It can affect it linearly with an exponent of 1. Right, concentration of A could have an exponent 1 relationship, whereas you change the concentration of A, it will change the overall rate of the reaction for the overall reaction by a certain exponent. In this case, if it's linear, it would have to be 1. Or you can change it exponentially if the exponent is 2. I know it's a bit out of context, but try to follow along. We're going to get to an example that will hopefully put it together. Okay, so our rate is therefore expressed in a different way. Our overall rate then of the reaction is expressed in this very simple reaction from A to B is expressed in this way, where rate is equal to or proportional to the concentration of A. We'll talk about what's going to actually replace this, but the concentration of A to a certain exponent. Okay, so that's the idea behind rate law, is that the overall rate of the reaction is dependent on a reactant, in this case A, to a certain unknown exponent, which we will determine what that value is in these questions. Okay, again, a bit out of context, but we're getting there. Okay, to piece it all together, to compare rates of reactions, or the overall rate of the reaction, compare that to the individual reactants and products rates. This hopefully will clarify that. So the overall rate of the reaction is not related, like I said in a couple previous slides, it's not related to the coefficients in the stoichiometrically balanced equation. Instead, it is related to the exponent and to the type of reactants and concentrations. Right. So that exponent. So in the case of that general A to B reaction, that exponent unknown here, that's what we're going to try to solve for, because this is proportional to rate, okay, to a certain exponent. Okay, and this is what it looks like more formally. So the rate of the reaction is actually equal to, in a more general form, A plus B react to give you C and D, right? Where we're really just looking at the reactants, because that's what our rate law says. It's dependent on the reactants. So for the moment, we can ignore our products, right? More on that and as we begin our next unit. But for now, we're going to look at just the reactants. So the overall rate is dependent on the reactants A, B. Now there could be more. It could be A, B, C. Um, and they have certain exponents. We'll call them M and N. It is our job then to determine what that relationship is. Is it linear? Is it exponential? What are the values of M and N? Also, that's the first thing. Also, what is the value of this K? Okay, this is a constant. It will have certain units that we'll get into discovering how or figuring out how we can determine. Right, so this is your called your rate constant. Okay, so let's look at this balanced hypothetical reaction. Right, notice I've just written products for the products because we know that for now they don't really matter. We're just going to write products. If our reactants affect the rate of the overall reaction, or in this case reactants A, B, and C, look at how they're balanced: 2 to 2 to 3. And turns out through experimentation that the rate law happens to be this. So this is the rate law. Rate law is written, you write rate, you write equal to, you write K as your rate constant, and then the concentration of A, in this case, through experimentation, this particular example is going to be to the power of 1 for A, and B will affect the rate exponentially to the power of 2, and C, concentration of reactant C, will affect the rate to the power of 0, which really means it has no effect. Notice though, I wanted to point this out, the exponent is 1. That's not what the coefficient is. The exponent here is 2. Yeah, that happens to be what the coefficient is, but that's not, there is no relationship, no direct relationship there. This is 0 and there's a 3 here, so it's not, these coefficients don't have anything to do with the exponents. Unfortunately, it's not that simple. Okay, so let's continue with an example. All right, with this same one, we're now looking at what these exponents actually mean. All right, so reactant A, if you then if you double the concentration of A, what do we then expect the rate of the overall reaction to do? How will that change? Now look at the exponents and consider if you double A, so if you've doubled A, started off as 1, if you double it, and if that has an exponent of 1, what have you done then to the rate of the reaction? It has also doubled because it's a linear relationship. Okay, now for B, what will happen to the rate, right? B has an exponential relationship. If we double B, so let's say it was 1, we double it. Oh, sorry, you're looking at this and you're hearing me say double, and it's not really being doubled, it's being tripled. All right, let's fix that. So if we triple the concentration of B, knowing that it has an exponential relationship, exponent of 2, 3 times 3 is then 9. So the rate of the reaction is going to change by 9. Right? Be careful. Sometimes it's a common mistake. I'm sure you know not to do this, but it is common to think 3 times 2 is 6, but that would be wrong, right? 3 times 3 with an exponent of 2 is 9. Okay, sorry, I'll rephrase that. 3 to the exponent of 2 is 9 because 3 times 3 is 9. All right, so C. C, we know, has no effect on the rate of change or the rate of the overall reaction. So if we quadruple this, it's really 4 to the power of 0, which is just 1. There really is no effect. So no effect on the rate of the reaction. That hasn't changed. Okay, so hopefully that can piece together what a rate law really means. Now, we can talk about rate law, and you talk about it a certain way. You say it a certain way. This will represent something that can be said a certain way, and this is how you would say it. So your rate law, the different parts of it. Your rate law is, let's begin with K. The overall rate is dependent on K, a rate constant with unique units. A in this case is, now this is where I want you to pay attention. A is first order because it has an exponent 1, so therefore it is first order. The reaction is first order with respect to A. So the rate of the reaction is first order with respect to A because of its exponent. B, the rate of the reaction is second order with respect to B because of its exponent. The rate of the reaction is then not dependent on C also because of its exponent, in this case being 0. The last thing we should talk about is the overall reaction is then third order overall. All you do then is add the exponents. So 1 plus 2 plus 0 gives us 3, of course. So it's third order. When we would say the overall order of the reaction is third order. So it's a third order overall. Okay. So be a great communication piece, a communication question. Just how would you how would you communicate a rate law in words? How would you describe a rate law? Okay. Now, these are steps. We've often had these steps, just I'm not going to spend a lot of time on it. Sometimes I do, I focus in on something, but with this being out of context, I think this is best used as a reminder of how to solve problems that you can look back at as you're solving them yourselves or as you're practicing. So let's start with our example. Okay, so here we have a bunch of data. I'm going to hide that for now so you don't hopefully get too overwhelmed. So this is a reaction. Right? It looks like it's an ionic reaction here. Um, a total ionic reaction or net ionic reaction. We have iodate, iodide, hydride ions all react to produce iodine and water, right? So it's asking us to do two things, not just one. It's asking us to find the rate law and the rate law constant. That's K. Okay, with their units, with its units. Okay, given the following information. So rate law. All right, I'm going to reveal this, but let's just go over what rate law means. Okay, so it will be rate is equal to a constant K that will have units that we have to figure out. Now in this case, all of our reactants are going to be part of that rate law. So IO3, that's a 3, negative will have a certain um, exponent. We'll call that M, trying to follow the convention here. And then iodide will have a certain exponent N. And in this case, we have a third reactant. Let's follow the alphabet here, MnO. It will have an O. Maybe not the best exponent to use since it looks like a 0, but if it were a 0, put a line right through, so it's an O. So we're going to find MnO. I've recalled now actually seeing different letters for these exponents, but MnO is fine for now. All right, so we need to figure out these exponents. Okay, now how we do that is we compare all of our data. So we need to figure out what the relationship of the concentration is to the rate of change for each of these. So to do that, let's start with iodate. If we change the concentration of iodate, let's compare trials 1 and 2. I just start off by comparing 1 and 2. I'm really going to spend some more time, you'll see, looking at which two trials we need to compare, but part of our rules on the previous slide says compare two trials, where if we're testing for iodate, for example, we're looking to make sure that the other reactant concentrations stay the same. They have to be our controls. If we're to determine how the concentration of one affects the overall rate of the reaction, well then we can't have anything else changing. Right? These have to be our controls. So in this case, it works to compare trials 1 and 2. By comparing 1 and 2, we can see that if we've doubled and everything else stays the same between trials 1 and 2, what has happened to the rate? Okay, so you can look at this, and a lot of you will be able to see this and say, okay, I know it's doubled. It's gone from 5 times 10 to negative 4 to 1 times 10 to negative 3. It's doubled. Now, if you're stressed, or if you're just a bit anxious during a quiz, test, or exam, then all you do is take the bigger number and divide it by the smaller number. You're going to get 2. Okay. Now, what that means is, as we're comparing trials 1 and 2 for iodate, um, The conclusion then that can be made is when iodate doubles, the rate also doubles. It's therefore first order. So think about it this way. If we've doubled the concentration, what is our exponent? First, what happens here? Turns out the rate doubles. So 2 to the power of, or 2 to what exponent gives you 2? Okay, there's some great ways of solving this using a bit of math, but this is it's simple enough that you can just figure this out yourself through trial and error or just by thinking about the relationship. You can use ln. I'm not going to get into that right now, but that's probably the best way to do these types of questions. But it being just this not too complicated a number, n needs to be 1. So it has to be 1. M has to be 1. So 2 to the power of 1 gives you 2. 1 is then the exponent. So first order in this case with respect to iodate. Okay, so we know the exponent for iodate. Okay, oops, eraser, right. Now we have to compare, figure out iodide. I know the answer is there. I go through the logic, but let's do the next one, iodide. Okay, so iodide has to change. Iodide has to change. Don't know why it's, oh, let's select that. Oh, that's weird. Okay, I'll stick with this. Okay, so iodide has to change. We're going to compare, let's see, trials 1 and 3 maybe. Look, it's gone from 0.1 to 0.3. All right, so it's tripled here. That could work. The other reactants have to stay the same. So 0.1 to 0.1, that's perfect. 0.1 to 0.1, that's perfect. So good. We're going to now compare trials 1 and 3. So what's happened between trials 1 and 3? Let's look here to there. Okay, so if it's not entirely clear at first, all you do is you take the larger number and divide by the smaller one. And you can then figure out what your exponent is. So I'm going to put a shade here so we can concentrate on just one. Okay, so we're comparing trials 1 and 3. Iodide changes, right? It triples. Okay, turns out the rate also triples. So our exponent n as our unknown would then need to be 1 as well. N has to be 1. So the reaction is therefore first order with respect to iodide. So far our first two reactants are all first order. Okay, let's do the next one, the last one. All right, now we're going to compare two trials. Let's figure out which ones those are. All right, let's try 1 and 2. That doesn't work. If we're looking to compare, figure out what the relationship of change in that concentration is, it has to actually change. So what can we do? Can we compare 1 and 4? All right, let's see. Maybe we have to check out, look at the other reactants. Have they changed? This has changed. This hasn't. We can't do 1 and 4. Looks like, right? Because the other reactant has changed as well. That's not going to give us any conclusive results. Okay. What else can we do? Can we compare 2 and 3? Nope, that needs to change. Can we compare 3 and 4? All right, let's see if that works. We're comparing 3 and 4 where we're doubling here, and the other reactants stay the same. Perfect. Okay, we're now going to compare trials 3 and trial 4. Good. That means we're going to compare these two rates. Okay, take this number, the large number, divide by that. If it's not entirely clear, you know that if you've doubled, what's happened here? You'll notice it's quadrupled. Okay, so we're comparing trials 3 and 4. Right, and every other concentration for every other reactant then stays the same. When hydride doubles, the rate actually quadruples. So let's look at what that means. So if we double, and this is our exponent, I'm going to use question mark, that 0, I don't like how, or that O, I don't like how that looks. What is in the exponent here if we end up quadrupling the rate? Well, it has to be a 2. That means it's second order with respect to hydride. Now, let's put all that together. We now know what all of our exponents are. Rate is equal to a constant K, iodate to the 1, iodide to the 1, hydride to the 2. Right? Part A is done. Oops, didn't mean to do that. Part A is done. Okay? Moving on, though, we need to figure out what our units are for k, right? So solve for k. Now here, what you can do is plug in values for any of the trials. So you want to plug in a rate value and units. You want to plug in concentration and their units. So I like to choose the easiest one. Why give yourself more work? Trial 1 seems to be simple enough. 0.1, 0.1, 0.1. Look at the concentrations. It's not moles per liter, it's millimoles per liter, right? So consider that. The rate of production of iodine here, that is millimoles per liter per second, right? So remember those units. These values are all going to be plugged in. We're just doing trial 1, right? We should get the same result for any of the trials. Let's choose the easiest one, all 0.1 across the board, so let's do that. Okay, this is our rate from our table, right? These are concentrations, all the correct units. Turns out this is what we get, right? So our rate constant is K, and these are the units. Now, this involves a bit of grade, I think it's grade 9 math, grade 9 or 10 math, exponent laws. I'm going to say grade 9. It's been a while. Let's see. Let's solve this. Okay. We have, forget about the numerical answer here. That's easy, right? We have millimoles per liter per second. And we're going to divide, right? Millimole times millimole is millimole squared times millimole to the power of 2, because that 2 carries into the brackets, right? So that's 2 millimoles plus 2 more moles. That's millimole to the power of 4. I'm leaving out liters here, but it's millimoles per liter times millimoles per liter times millimoles per liter. Both of those are squared, so it's actually millimole to the 4 and liter to the 4. Well, we know that if we divide a fraction, it's the same as multiplying by its reciprocal. So what we get is millimole per liter per second times liter to the power of 4 and millimole to the power of 4. Now, look how our units cancel out. Liters cancels out at the bottom here. That means we're left with 3, right? 3. Millimole at the top, that completely cancels out, and we're left with a 3 here. Turns out those are our units. Okay, just a bit of review from grade 9, 10. Or rather not, try not to memorize. You have enough to memorize, right? Or just look at this table. So there is a bit of a pattern you can probably figure out. Any reaction that is 0 order overall has these units, moles per liter per second. That should make sense. It's not dependent on any of the reactants. Is it even a reaction? I don't know. First order is 1 over s, and then your values just tend to, your exponents tend to increase. Now liters appears, then it's mole per second, then it goes liters squared over mole squared per second, and that pattern continues, right? You don't need to memorize. Math saves a day any day. Okay, that is rate law. Here is your home fun. Practice it. You've done, I think, harder things in this unit so far, but it does require practice. Ask any questions. Hope this helps.